Hi everybody. So today we're talking about the Math 17B discussion sheet number 4. Okay, the first problem is about spatial variation of sodium channels in an axon. Suppose that you are measuring the spatial variation of sodium channels in an axon in a nerve cell. So the picture looks like this. Here's your axon in a nerve cell. To do this, you add a fluorescent label to the sodium channels, and then you use a microscope and camera to capture an image of the axon. The camera collects light, and by measuring the intensity of light in each pixel, you can determine the number of sodium channels that are present. Thus, for example, you determine that there are 19 sodium channels in the first pixel, which is 50 micrometers wide. Therefore, there are 19 channels in the first 50 micrometers of the axon. The rest of your measurements are shown below. So first, in the first pixel, or 50 micrometers, we count 19, then 17, 14, and so on. You find that these data are well fit by the following equation. N of L is 120.78 e to the negative 0.1 L over 1 plus 5.06 e to the negative 0.1 L, where N is the number of channels per 50 micrometer pixel, and L is the distance along the axon in micrometers. Okay, so if we go to this next page, they give us a nice picture. So the picture shows us that as we move along this axon, we count 19 micrometers, and that's in the first 50, right? So it's not this isn't a continuous measurement. This is a discrete measurement. So in this first 50 micrometers, we count 19. Then in the second 50 micrometers, we count 17 and so on, okay? Now, they want us to calculate the number of channels in the full length of the nerve cell given the best fit equation. So the best fit equation is a continuous function. So that's given in this black right here. So what we want to do is we want to integrate N of L with respect to L, but then we have to remember that every time we measure N of L, we're counting an estimation of number of nerve cells per 50 micrometers. Sorry, a number of sodium channels per 50 micrometers. So to get the correct answer, we need to divide by 50 at the end because we've overcounted every time we accessed N of L. Every time we measured N of L, we were counting for 50 micrometers. So since we did that over the whole length, we need to divide by 50 at the end. Okay, and we need to figure out where to integrate. So we're going to integrate from length 0 to length 1,000. So always remember that when you're integrating, you should look to your integrating variable with what variable with respect you're going to integrate to get your limits. So since we're integrating with respect to length, we go from 0 to 1,000. That's the length of the axon. Okay, so now if we bring in some paper to do this, so we're going to get the integral from 0 to 1,000 divided by 50 of N of L, which is 120.78 e to the negative 0.01 L over 1 plus 5.06 e to the negative 0.01 L dl. Okay, so let's integrate this. So I'm going to make a u substitution. U is going to be 1 plus 5.06 e to the negative 0.1 L. Then that means that du, we take the derivative of this 1 goes away. We bring down a negative 0.01. So we get negative 0.0506 e to the negative 0.01 L. That stays the same, dl. Okay, so notice that's what's on top here is almost our du. It's just differing by a constant. Okay, so now I'm going to write this integral without the bounds, and I'll bring the bounds back at the end. So notice I don't say that these two things are equal. They're not equal. I am just simplifying for the purposes of using my u substitution right now. Okay, so this is 120.78 over negative 0.0506 times negative 0.0506. So notice how I force the constant that I want here, du, to show up. I write it and I divide by it. So this is just multiplying by a form of 1. E to the negative 0.01 L dl all over 1 plus 5.06 e to the negative 0.1 L. Okay, so now we can clearly see we have a constant that we can bring out front. And then we have the integral. Now sitting here, once we pull the constant out, is just du over u. Okay, so this is 120.78 over negative 0.0506 natural log of u plus some constant. Okay, so remember I didn't write that these two things are equal. Right now I'm just evaluating the indefinite integral, and then I'll bring the bounds back for the definite integral once I replace everything back in. Okay, so now this is equal to 1 over 50 times 120.78 over negative 0.0506, and then I've integrated here, and now I plug my u back in, so I get natural log of 1 plus 5.06 e to the negative 0.01 L. Okay, and then because I have bounds that I'm evaluating, I don't have this plus c. That goes away because I'm now doing a definite integral. Okay, so this is my solution, and to complete this problem I would plug in 1000 and evaluate this value, and then plug in 0 and subtract that value. Okay, so that's part A. Part B asks, according to your measurements, how many channels are there? So remember that our measurements from before were just literally counting the number of channels per pixel. So because we measured all of the pixels, we just need to count up all of our counts. So our solution here is 19 plus 17 plus 14 plus 11 plus 8 plus 5 plus 3 plus 2 plus 2 plus 1 plus 1 plus 1 plus 1, and that's it. Okay, so this is my answer if I were to add it up. Okay, now it asks, which estimate, A or B, would you expect to be more accurate? Briefly justify your choice. This one really depends on what you think. I don't think that there's a correct answer in this case. Maybe there is if you know how this stuff works, but clearly we've counted the number of channels per pixel, but we didn't count them exactly. In the description of the experiment, they say that they they measure the light coming out of the pixel in order to measure how many channels are there. That might not be exact, so maybe we would expect that there was some error there, but then when we made a best fit, maybe we really expect that our data should really fit this best fit line, and when we integrate the best fit line, we actually get something better. So it really depends what you think. This depends on how well all of these measurements work and what our model should actually fit to. Okay, the second problem is about calf pneumonia. Calf pneumonia is a major problem in dairy and beef herds. It is a multifactorial disease and the most common post-mortem diagnosis in calves between 1 to 5 months of age. An animal scientist measures the probability that a calf in a certain herd will die at age t months by the formula P of t equals 0.2 lambda squared t e to the minus lambda t, where lambda is a parameter that's somewhere between 0 and e. Okay, so say a herd is showing a maximum likelihood of calf pneumonia death at 2 months, and the probability of death at this age is 4%. Using the RStudio code below, find the lambda that will best fit P of t to the data. So what this means is that we'll plot P of t given a bunch of different choices of lambda and figure out which one gives us a maximum. So the peak of one of our curves should occur at 2 months and 4% or 0.04. Okay, so we're going to do this in RStudio. Okay, so we need to plot and figure out which value of lambda fits our data best, or gives us a peak at 2 months and probability of death 4%. Okay, so to begin with, we'll define our vector t. So t is going to be our measurement of time. So we're going to measure from 0 to, and here you could really choose anything. I'm going to choose 12 months because of the second problem. It asks us about a calf age 6 months and a calf age 1 year old. And then I'm going to measure by 0.1, 1/10 of a month. This choice is just so that I can see a little more clearly what's happening. You know, it captures the curve a little bit better. Okay, so there's my t vector. Okay, now I'll define my first guess for lambda. L is going to be 0.5. I'll define p, so it's 0.2 times L to the second times t times the exponent of minus L times t. Okay, so now there's my p vector. So now all I have to do is plot. So I'm going to plot t, p, and I'm going to tell it to plot it as a line. Okay, so now I see my nice curve. Notice I'm really close. This is almost happening at 2 months, and it's almost 0.4. It's a little off. And actually, if you mess around with it a little bit and end up with L equals 0.54 or lambda equals 0.54, notice you have to redefine P, otherwise it won't change P. And then now you plot, and you get exactly what you want. So at 2 months, we're right about at 4%. Okay, so our choice should be about 0.54 for lambda. Okay, now looking at our plot, we can answer part B. It says, in your best fit plot, what is the probability that a calf aged 6 months will die of pneumonia? So at 6 months, we're at about 0.013, which is 1.3%. So I'd say it's about 1.3%. And then for a calf that's 1 year old or 12 months old, it's at about 0.001, which is about 0.1%. Okay, part C asks us, in the model P of T, what is the total percentage of calves that die of pneumonia? So a lot of people had some interesting points for this question. So we do say, what is the total percentage of calves? But we actually intend, you know, at any age, what is the total percent, or what is the probability? P of T is true for any T. So not only when calves become cows, we still count that. So we go on through their cow life, and we even go past that. So for example, in our model doesn't know that cows can't live to be 1,000 years old. So there is a very small but non-zero probability that a cow will die of pneumonia at age 1,000 years and at age 1,000,000 years. Okay, so this while being very interesting, it doesn't take into account the fact that cows can't live forever, and there's always a probability that's non-zero that a cow will die. So in order for us to find the total percentage of calves that die of pneumonia, we have to integrate not just from 0 to 6 months or 2 years when calves are supposedly cows, but all the way up to time going to infinity. Okay, so in this problem, we're going to integrate from 0 times 0 when calves are born to infinity of P of T, which P of T is 0.2 lambda squared t e to the minus lambda t, and we're going to integrate with respect to time. So since this is the probability that a cow dies, if we integrate overall time, we get the percentage of cows that will die total. Okay, so again, I'm going to do the same thing here, except for instead of u substitution, I'm going to make integration by parts, and I'm going to forget about the limits of integration for a second, and instead I'm going to compute an indefinite integral, and then I'll come back and evaluate the actual definite integral once I'm done. Okay, so instead of this, I'm going to pull out 0.2 lambda squared, and I'm going to, and actually I'm going to forget about that completely for the moment, and I'm just going to integrate t e to the minus lambda t dt. I'm going to do the indefinite integral, and then I'll do the definite integral. Okay, so here I'm going to make a integration by parts. So I'm going to choose t to be my u, okay, and then I'm going to choose dv to be e to the minus lambda t dt. Now when I integrate this, I get v is minus 1 over lambda e to the minus lambda t. Now this minus 1 over lambda comes from the fact that when I take the derivative of this, I pull out a minus lambda, so those will cancel to be 1, and I'll end up with just e to the minus lambda t dt. Okay, now du, is easy, it's just dt. Okay, so then using the integration by parts formula, I get u times v. So this is minus 1 over lambda t e to the minus lambda t. Okay, so that's uv minus the integral of v, which is minus 1 over lambda e to the minus lambda t du, which is dt. Okay, so simplifying, this is minus 1 over lambda. This doesn't simplify, e to the minus lambda t. Now this minus a minus becomes a plus. And when we integrate the e to the minus lambda t, we pull down, just like before, another minus 1 over lambda. So I get a minus 1 over lambda squared e to the minus lambda t. Okay, so this is my integral. Okay, and now I want to perform the definite integral. So I'm going to bring this down. This is 0.2 lambda squared times this integral, minus 1 over lambda t e to the minus lambda t, oops, and I'm going to make this a minus 1 over lambda squared e to the minus lambda t, evaluated from 0 to infinity. Okay. So now we just have to write out what this means. This is 0.2 lambda squared. I'm going to pull out this minus 1 over lambda, and now I'm going to do the limit. So this is the limit as t goes to infinity of t e to the minus lambda t, which I'm going to write as t over e to the lambda t. Okay, and then notice when I plug in 0 here, I get t equals 0. That just goes away because this e to the minus 0 is going to be 1, so I just get 0. So I'm not going to write that one. This when I plug in 0, this evaluates to be 0. Okay, minus 1 over lambda squared. Now we have a limit. The limit as t goes to infinity. I'm going to write this e to the minus lambda t as 1 over e to the lambda t. And then I have a plus because I'm subtracting this lower limit of a minus. So this is going to be a plus 1 over lambda squared. Now when I plug in 0 here, I get e to the 0, which is 1. So this is just plus 1 over lambda squared times 1. Okay, so now all I have to do is evaluate these limits. Now this limit, as t goes to infinity, this top goes to infinity, the bottom also goes to infinity. So I have an indeterminate form, and I'm going to apply L'Hopital's rule. So this is 0.2 lambda squared minus 1 over lambda. This, when I take the derivative on the top, I get 1. When I take the derivative on the bottom, I get lambda e to the lambda t. Okay, minus 1 over lambda squared. Now this limit, as t goes to infinity, I get 1 over infinity. This is just going to 0, plus 1 over lambda squared. Okay, now notice taking this limit, I get 1 over lambda e to the lambda t as t goes to infinity. This is 1 over infinity, which is going to 0. So I get minus 1 over lambda 0. And this 1 over lambda squared times 0 is 0, and then plus 1 over lambda squared. So this whole thing is just 1 over lambda squared. So I get 0.2 lambda squared over lambda squared, multiplying it out, which is just 0.2. So in other words, the total percentage of calves that die of pneumonia is 0.2, or 20%. Okay, that's the total percentage. Then part D asks, based on your answer to part C, if we wanted to model a population that had a total percentage of pneumonia death at 12%, what would the equation be for P of T? So notice this 20% exactly corresponds to this 0.2. This 0.2 just like went along for the ride the whole time. The other stuff integrated to be 1. So if we want to have instead a total death of 12%, we would want this to be instead of 0.2, 0.12, 12%. Okay, so P of t, so for part D, P of t is 0.12 lambda squared t e to the minus lambda t. That's the answer for part D.